Section 4.4 is called the definite integral, and we're actually going to start this section by talking about a little bit of vocabulary and a couple of theorems that are going to be coming into play that we'll be using in a variety of different examples as we work. So here's our first definition that I referenced. We're going to talk about a function. Our function is going to be defined on an interval AB, and we're going to talk about what a definite integral is. So a definite integral is this description right here, this image, or this script S, like we've seen before. And it goes from A to B of f of x dx. That notation, let's just talk about that piece right there. That should look very familiar. It looks awfully similar to what we did in section 4.1. What's different? The B and the A, right? The B and the A are different. So what's going to end up happening is that the B and the A are going to affect the problem in a little bit different way. But if you'll notice, what they're actually referencing is they're referencing an interval. An interval, it starts at A and it ends over here at B somehow. Now the other half of this tells you what this is, the value, how to get the value of this thing. This is a limit. Now we just talked about limits, right? Just a moment ago with these rectangles. It's a limit as n goes to infinity of the summation from I equal 1 to n of this notation. So take a look at this. This notation came about in the last section, the one that you guys watched, right? F of c sub I, those are the heights of rectangles. Delta x over here, that's the width of the rectangles, they're all the same. So all this is doing is finding areas of rectangles. That's what the summation does. The difference between this and what you did is that this goes from I equal 1 to n, and n's going to infinity. This is a limit instead, right? It says because as these rectangles become infinitely narrow, that is, they become infinitely more rectangles. So what this is telling you is it's telling you that this thing called the definite integral, which we're going to write it like this, can be found by doing this limiting process on areas of rectangles. That's what this is saying. Whenever the limit exists and is the same for the choice of evaluation points, these C1 to Cn, these are just the heights of your rectangles, right? The x values of the location for the height of the rectangle. Remember I told you how the left endpoint and the right endpoint and the midpoint all sort of converge to the same point? That's what that's referencing, okay, the height of wherever that rectangle is. It's the function value at that x value Ci. And when that limit exists, we call f integrable on AB. That is, we are able to find an integral of it. You've heard the phrase differentiable before, right? Meaning able to find a derivative. Same idea. So one of the ways that we can find out if a function is integrable is whether or not it's actually continuous. And that's our first theorem. Our first theorem says that if you have a continuous function, what are some continuous functions that we've worked with and you guys know? Like general types. Sine and cosine. There's another type that we've worked with on and off throughout the semester. Polynomials. Those are the two. Those are the two most common ones that we've been working with. So all of those types of functions are going to be integrable because they're continuous. Okay? And really, it's just continuous on an interval AB. So some of the other functions that you know, things like tangent or secant, those have portions of the graph where they're continuous, right? Portions that don't include the asymptotes. So if you just use those portions of the graph, you've also got an integrable graph for those. Now, if you in fact have a graph that's integrable, or function that's integrable, you've got these couple of properties down here. Now, these couple of properties, at least the first one, let's talk about it. This first one will should look very familiar, because what's going on here in this property, we've seen happen time after time after time in calculus. The first place we saw this property happen was with limits. And then the second place we saw this property happen was with derivatives. And then the third place we saw this property happen was with these summations, most recently. So this actually is telling you that if you have a constant times a function, or if you have the sum of two functions, that you're able to separate the integrals apart. In fact, we saw it with integration for indefinite integrals in section 4.1 as well, just a few days ago. So if we have a function and it's got a constant multiplier, you can pull the multiplier in front. The c can come out to the front, just like this d can. And if you've got the sum or difference, it could be difference, you can separate them completely so that you take the individual indefinite integral. That's what we did it with before. In this case, we're doing it with definite integrals on those two pieces of the function. So we can separate it. That looks familiar, right? We've seen this happen on multiple occasions. This next one down here feels a little bit awkward, but all this is saying is that if you have a point between A and B, okay, that you could find the integral from A to that sort of in-between point, C, and then you could find the value from that point C to the point B. And the reason that that's happy and helpful is there are some functions that are not continuous that we can do integrals for, but we kind of have to break them into pieces. Like imagine that you had, I'll draw the picture up here so you can see the number line of what I'm thinking about. So here's A, and here's B, and somewhere in between is the point C. What if the function were continuous everywhere but C, like it has a hole in the graph at C? Right, so maybe the image goes something like this. Well, it is perfectly fine according to this, oops, I didn't quite get it all the way over here. According to this last theorem, part 2 of this last theorem anyway, that we could find the area from A to C, right? And then we could find the area then from C to B. And we could add them together. Visually that makes sense, right? You just break it into a couple of pieces and you find the pieces that are easy to work with or easier to work with, and then you just work with those pieces and add them together when you're done. All right, so the rest of the different pieces of this section that we're going to do, the examples, are going to feel a little bit disconnected, but they're each giving you a sort of a different component of the idea behind what definite integrals do. So all definite integrals actually are is really finding the area under the curve. We approximated it in 4.3 with these rectangles, but now we're going to let these rectangles get infinitely small so that we really actually find the actual value of that area. Make sense so far? All right. So this is a function we're going to work with, x cubed minus 1. If you have your calculators, it's going to help you to take a look at some of these functions, and I'll draw them here as well. If you don't have them with you, it's okay. And to give an interpretation, it might be helpful to see the picture. So this graph is the graph of x cubed minus 1. Notice the limits of integration, 0 and 1 here, or 0 and 2 here, excuse me, tell you how to set your window of your axis so that you can see the picture of the graph that you're supposed to be seeing. So if you take your calculator, go ahead and put this into y1, the x cubed minus 1 into y1. And then I want you to hit window and have your x minimum be 0, x maximum be 2. And then in terms of your y-axis, if you actually hit zoom 0, then it will automatically set your y-axis so that x-axis values from 0 to 2 are how it determines a good y value. It's a really handy feature. It's called zoom fit. Zoom 0. It's called zoom fit. So it fits the y-axis to whatever x-axis limitations you gave it. Does everybody see an image? If you have a calculator anyway, you do see something? So it looks something like, make sure I got mine, like this. Does that look right? Okay, good. Let's get some details on here just so that it makes sense. Where is it hitting the y-axis? It is over here. Where am I? -1. Thank you. It's not a difficult question. You just put in x equals 0. You plug x equals 0 into the equation, you get -1, right? Now, we're going from 0 to 2. So if you put x equals 2 into the equation, it tells you sort of the height that you're at on the other end of the graph. So if you put in x equals 2, what do you get? 7. Thank you. 2 cubed minus 1, 7. All right, so if we're finding trapped area, we're always finding area from between our curve and our x-axis. So if we went from 0 to 1, we'd be finding this piece down here. Okay? And if we go from 1, this is actually 1. I didn't make mention of it, but it does cross the axis at 1. If we go from 1 into 2, we find this area over here. Is everybody good so far with that idea? It always finds area between your curve and the x-axis. Here's the deal, though. It actually finds the area as a signed area. I actually chose these colors on purpose. This piece right here, if you find this exact area with the formula that we had back on the very first example and so forth, and with the rectangles and all that good stuff, it will tell you this area is negative. And the reason it does it is because it's beneath the x-axis. I mean, that's why. So it would call this negative area. I know that feels weird to sort of even talk about in that way. But it would call that negative area. And this piece would be considered positive area. So if you actually find the area from 0 to 2, what will actually happen is that some of that positive will be negated by some of the negative. It adds them together in kind of a way that's like a net area, right? It's kind of like if your bank account had negative $5 in it because you overspent something and you went and you deposited $25. You don't have $25 really in there, right? You just have 20. That's what's happening here. It adds as it moves from left to right. So from moving from left to right, it's got negative area until it gets to number 1, right? Like the negative bank account. And then from 1 to 2, it starts compensating for that and adding that back to that negative value. So somewhere between 1 and 2, like right about here, we're going to hit it with a 0 area. Okay? Now, the question's actually asking us to give an interpretation for what's going on this integral. What kind of phrases come to your mind or ideas come to your mind when you're asked to interpret something? What are they asking you to do? What does interpret mean? Explain. And explain usually means use words, right? It wants you to write a description, an explanation, to explain in words what's happening. So let me give you an example of one. You can write your variation of this, and that's fine. But you're going to describe in words what happens. So when these two pieces of area get added together, quote unquote, actually what you're going to end up having is not a total area, right? You're going to have something that I referred to as net area. So I want to sort of describe that in a way that will make sense in terms of the area. So what I'm going to say is something like this. This is the difference in the trapped area, or let's say area trapped. The area trapped between the curve and the x-axis from 1 to 2, and the area trapped between the curve and the x-axis from 0 to 1. That's what it is. It's the difference. It's the difference in the area that's in black and the area in red. And difference means subtraction. It's taking this area minus this piece, which is why I'm using that to be negative. That's a way of thinking about it. It's subtracting this area minus this area, that one that's in red. Does that make sense? There are other versions of this kind of a description. You can see how your book phrases things as well if you'd like. I think there's an example in your book where they're asking an interpretation kind of question, like they give examples. So if you want to model it after their phrasing, that works too. All right, let's take another example. These next two are a little bit more straightforward. They don't require us to use words. So this one says to write the given total area as an integral or sum of integrals. Okay. Now, in order to do this, you'll notice on this one it says the area above the x-axis and below the curve. It doesn't give you any starting point and ending point, does it? So you're going to have to look at a calculator, or you would have to actually do some calculations with some algebra to figure out what is my starting point and what is my ending point. And a graph is a really helpful way to do this. So go ahead and grab your calculator, graph 4 minus x squared. And somebody give me a word picture that is described to me. What in the world does this look like? What is this a graph of? What's the shape? Do you want to say it, Micaiah? It is a parabola. How can we decide that based on the equation? Because it's got an x squared in there. Yep, this is a parabola opening downward. And it opens downward, and it looks something like this, I believe, in your calculator. Does that look pretty close? So do you see the area that is above the axis and below the curve? Can you see it? It's actually trapped, isn't it? So the area that they're referring to is this piece right here. But what we want to know is we want to know where does it start, that is along the x-axis, and where does it end along the x-axis? Can you tell from your computer or from your calculator screen? Or maybe doing a little bit of algebra to do find out where this thing is equal to 0. What values will we get for this function 4 minus x squared to equal 0? 2 and negative 2. So this starts at 2. Right here's negative 2, rather, and it ends at positive 2. All right, so this will be an integral of our function. And just like in section 4.1, if you've got an integral sign, you've got the dx, right? And this has the parentheses around it. It starts at negative 2, and it ends at positive 2. And that's all they asked for in this problem. That's it. There's no other pieces or anything like that. The piece that you needed the graph for is to simply get the limits of integration, negative 2 to 2. Does that make sense? Okay, let's take a look at another one. This one wants us to sketch the area corresponding to the integral. This is almost like the exact opposite question of number 2. They give us this description, right? And we're asked to sketch the area. So you've got x squared minus x that's going to go into your y1 in your calculator, x squared minus x. And then I know it says that we're going to go from 2 to 4, and that's fine. But it might be helpful to actually look at the graph going from 0 to 4. It's really hard to gain perspective of a graph when you can't see one of the axes. Does that make sense? It just sort of looks like it's hanging out in there and you don't know how far up or down or anything you are looking at the picture of it. So go ahead and graph your calculator going from 0 to 4. And we will recognize that our graph will start at 2 and go to 4. Okay, that's the part that we're actually going to be caring about shading. So what is this an equation of? Look at the equation. What kind of graph am I getting? It is a parabola opening up this time because the x squared is positive. And if you look carefully, the graph looks something like this. Is that pretty close? Look all right? Sketch. Just for reference points as well, how high does this go? It will go as high as you get at x equal 4. If x is equal to 4, what do you have? 12? Okay. And at x equal to 2, just so we have a reference point, what would you have? 2? All right. This is what we have. We are supposed to sketch the area. Right now I don't have any area. I've just got an equation, right? I'm supposed to sketch the area that starts at 2 and ends at 4. So I'm starting at 2 here. I'm ending at 4, and I'm asked to sketch this area in here. That's it. Does that sound okay? You're just working the pieces in together. Next one. All right. This one says we're going to evaluate the integral using the following. This is the case where I want you to just hold tight. I know some of you know what you would be doing once you get to 4.5, and some of you might even be thinking what you would be doing without realizing that you are correct. What we're wanting to do is we're wanting to apply the theorems that we looked at before. Do you remember those theorems? The theorems told us how we could separate these particular pieces apart because they're added and subtracted, and how we could deal with the fact that there's a coefficient right here, right? That kind of stuff. So what we're going to do is we're going to use that theorem to separate this apart and then to calculate what we would be getting. So the theorem says that I can write this as how many separate integrals? More. There are 3. And there are 3 because there are 3 parts to it. Right? There's 3 separations with addition and subtraction. So I'm going to have 3 integrals that go from 2 to 4. They each need a dx on them. Well, I'll put the dx's in a minute so that I can space this out a little bit better. There's an integral here from 2 to 4. And then there's an integral here from 2 to 4. And notice the signs stay the same. So since this was subtraction of the x, it's subtraction of the middle term. This is subtraction of the 7, it's subtraction of the end term. Okay. Now anything that's not a variable can come to the front. That is, the coefficients that we have can come to the front. So this is a number 4. It can come out here to the front. This doesn't have a number. That means this is assumed to be like a number 1. So you could write the number 1 here if that helps you feel better about that, but you don't have to. This is a number 7, which I know it feels a little bit awkward to do it, but we're going to pull it to the front as well. So this 4 is going to be in front. You can write or not write the number 1 here, and then there's going to be a 7 in front over here. I'm going to go ahead and put my dx's in now that I know my spacing's going to work. And then the part that still stays inside is the variable part. So this is x cubed. This is x. And you can either write in the number 1 here because 7 times 1 is 7. Or you can simply leave it written just like that, which is fine as well. And if you leave it written just like that, you recognize that that's exactly how this last one's written anyway. So it'll be okay. Now all you're going to do is you're going to recognize that this piece, and this piece you know values for because they were given to you with the original problem, right? The original description above. What is the integral from 2 to 4 of x cubed dx? It's 60. So now we have 4 times 60 minus. What is the integral, minus 1, what is the integral from 2 to 4 of x dx? It's 6 minus the 7. And what is the integral from 2 to 4 of simply dx? It's a 2. So this becomes simply a problem with addition and subtraction, multiplication, potentially. In this case, we do have some multiplication involved as well. So we have 4 times 60 minus 6 minus 14. What does that give me? 220. It is 220. Very good. Obviously, you were given the information at the beginning that allowed you to do that. So that should guide you in how you're trying to manipulate these. You have to manipulate these to be able to use the given information. Make sense? You've got a couple of those in your homework. The last problem that we have is a little bit more interesting. It's going to require you to remember a little bit of geometry, but not a lot. I promise you'll be okay. It says use a geometric formula to compute the integral. And this particular one is 3x plus 4. What's that equation of? It's a line. So go ahead and graph that line either by hand or in your calculator. I want this equation to be graphed, though, really only from 0 to 2. So what is the, it's supposed to be going from 0 to 2. So what is the x value, I'm sorry, when x is 0, what is the y value? 4. So my y-intercept, excuse me, is 4. And when x is equal to 2, what is my y value? What is it? 10. So my equation is going to look something like this. And I'm wanting to shade in the area from 0 to 2. So I'll use red here. Of this shape. There are 2 ways that I look at this shape and think it could be calculated. So let me ask you guys. This is just a 4-sided figure. There's nothing really special about it. Do you know what it's called? It is a trapezoid. So one way to calculate this area is to look up or to remember how you find the area of a trapezoid. Okay, so I'm going to tell you how you do that, but then I'm going to show you another way that if you didn't remember things about trapezoids, you can still do this problem. So this area, right, which is what I'm calculating this integral to be, is this area from 3x plus 4 from 0 to 2. It's calculated as 1/2 the first base. It's called B1. I'll identify for you on the particular picture what these are, plus B2 times the height. Now, the kicker is that the bases are the parallel lines. So the bases here are actually what look like the two different heights. Okay, those are bases. So this over here we'll call base 1, and this over here we'll call base 2. So what is the length of base 1? And what is the length of base 2? 10. And then the height is this distance down here, which is actually 2. So you can use those pieces and you can plug them in. So this would actually be 1/2 4 plus 10 times 2, which would give me an area of 14. Okay, so is everybody okay? You guys probably remember that formula now that I mentioned it. It's probably not one that was probably on the forefront of your mind coming to class today, but it's not a very difficult formula. It's helpful to use. However, you could also have done this in a different way. Did anybody else think of this in a different way than trapezoid when I drew the picture? Sometimes it's helpful to break down a picture into pieces that you do remember formulas for. So what happens instead, what another way of doing this would be to break this into a rectangle and a triangle. So there's that rectangle here at the bottom, and then that creates a triangle at the top. And while you might not remember the area of a trapezoid, a little obscure, I am, okay, maybe like 95% certain you all remember the area of a triangle, right? And rectangles we always remember. In fact, we've already been working with rectangles in the last class session. So if you take a look, then we could talk about this being the area of a rectangle plus the area of a triangle. All right, so here's the rectangle at the bottom. How would I get the area of my rectangle? Yeah, length times width. So this is 4 times 2. The area of the triangle is 1/2, and then the base times the height. So what is the length along the bottom? 2. And then the other one goes from 4 up to 10, so we get 6, right? So this is 8 plus 6, which is 14. So there are 2 problems that you're going to work with in your homework. One of them can be done in a manner like this. The other one requires you to remember what the area of a circle is. What's the area of a circle? What's that? Pi r squared. Yeah, sorry, I just didn't hear you. Pi r squared. So you'll have to remember the area of the circle to do the other one. Any questions on this? This section feels like a lot of little bitty disjointed pieces, but they're all trying to develop your understanding of what this is actually doing when we calculate these, okay?